Okay, so last time on astronomy, in our penultimate lecture, with this one being our final lecture today, we talked about, oh, I sent you an email asking my, oh yeah, if you need to leave, that's fine because we're recording lectures, so it's not a big deal. I don't think we'll go. It's 3:30 now. I'm not really sure we're going to go that long, so it's probably. I would be surprised if we were still around at 5:55. Yeah. So, um, so anyhow, so we talked about the birth of the universe and how the universe came to be and what we can observe from the universe. But we sort of reached the limit of our understanding in terms of what we would call the standard model of particle physics. And that's what we call, that's the universe in which we can understand in terms of atoms and the regular subatomic particles we can create in a lab. Now, what's fascinating about astronomy is much like we were at the beginning of the course, we are in sort of the same place at the end of the course, which is we have this model, this theory that describes many things correctly, but there are observations that indicate that there is more beyond that model. We're trying not to make the same mistake that we made before in being sort of closed-minded about it, but it can seem that way because ultimately, fundamentally, we still use our tenets of science, which is that if the most chiefly among, well, one of the more chiefly among them, those tenets of science, is that we accept the easiest explanation for any given phenomenon. All right? And I want to be very clear that that doesn't mean that that explanation must be correct. We're just saying that's the accepted definition. More evidence, if the definition is not correct, more evidence should make that conclusion more complicated. All right? So in our final chapter, in our final lecture today, we're going to see how the universe shows us that there is more to the subject of physics and our understanding of physics than we can produce in a lab. And we can see effects, we can see data and observations that do not align or that go beyond what we would expect just a universe made of the matter we see and interact with. Okay? So, and today we talk about those observations from the current universe, and that will hopefully give us some perspective on why we have the universe broken up into the way we do when we talked about the development of the universe, right? In terms of those epochs of forces and things like that. So we have to look at two important observations or two important quantities that both have the word dark in front of them. So we're going to talk today about dark matter and dark energy. All right? So these, what we mean by dark here is that we can see the effects, but we don't see what's the underlying process. So here's what I mean. Imagine you have someone shows you a car of the future, right? Now, if someone pushes the gas pedal and the car goes, what are some assumptions you can make about that car? Or there's one real main assumption you can make about the car. That you can conclude is true. Does anyone want to take a stab at it? I'm asking a very generalized, broad question, so there's a few things you might get to. Fumes are going to come out. Good. That's a good place to start. What causes the fumes to come out? Fumes is an excellent place to start. Good. What causes the force is a good answer. That's there will be certainly some force, but what allows the car to exert a force on anything? Why is it when I push on the gas pedal the car goes? It's not just because of force. A force is created, sure, but what happens? Yeah, Margaret.
Professor, well, the car has gas.
Exactly. That's what I'm getting at. The car has to have gas or a battery, right? It has to have a fuel source. And whether it's gas or a battery, we understand chemically and physically how the chemical reaction allows energy to be available for the car to be the reaction that combustion or electrical discharge that allows energy to be available for the car to move, right? So when you look under the hood, you expect to see an engine that can combust gas or a battery, right? And that's what we mean by gas. Are you all with me there? Good. So when something is dark in physics, All right, it's as if we see the car going and someone putting the gas on the pedal on the gas, but we can't. But when we open up the hood, we can't look in the engine. We can't find the engine. All right, so we open up the hood. There's no engine. Now, some of you might be saying, well, sometimes the engine's in the back. So we open the trunk and we don't find the engine. So basically, we know there must be an engine because we can see this force being enacted and this energy being used. We can see the effects of this phenomenon happening. But when we look in the usual places, we can't find it. And every place we've looked for the makeup of dark matter or the fuel for dark energy, we come up empty-handed. We don't know. But we see but here's the thing. The car moving is an observation, not some theory or wild-eyed theory. There's observations that, about this large scale of the universe that compellingly predict the existence of dark energy. So we see a car moving. We're looking for an engine. We can't find the fuel source. We see the car moving, but we can't see its engine. With dark matter, we see things behaving in ways that aren't consistent with our the universe that only contains the matter, the baryonic matter is the technical term for it, that we're familiar with. And when we see it, we can see effects happening that aren't consistent, and so we say, well, maybe there's more matter. But then we can't find out what that matter looks like atomically. We can't create particles of this new type of matter. So we call it dark matter. So when we say something's dark, we can see its effects, but we can't look but whenever we look at the under the hood, we can't work out the mechanism by which it works. Okay? So now what we're going to do in this chapter is we're going to talk about what we know and conclude about dark matter and dark energy. And we'll go here to our definitions. It's just a nice picture. We're going to make some sense with this picture. Looking at the temperatures of gas nebulas can tell us a lot about dark energy. And we can see here about the unseen influences. I'll let you read those definitions, and I'll go over them a little bit. But I like teaching this particular topic for a few reasons that are personal to me. One is that when I was a student, there was only one good test for dark matter that I understood. That was like sort of, there really were two, but there was sort of one that people knew about. So dark, that non-astrophysicists or dark matter people. So when I was a student, there was exactly one. There was this indication that dark, and it's a pretty compelling one. I'll show it to you. That dark matter existed, but there were competing theories, right? There were competing ideas, and it seemed that they were not getting the love which they deserved. That maybe the universe just works in a fundamentally different way. And as a scientist, as I've become more mature, even though my intuition still doesn't like this idea of dark matter, I'm wrong, right? Like I've, as a scientist and a professional, had to be like, okay, so there are now 3 tests for dark matter, and they're all consistent with each other. That's a lot more compelling than one, and that kind of means that it's there. What dark matter is still very much debated, and there are no experiments to sort of give you an aha moment, but people are trying to develop that, and that's one thing we can see about science. I'll get in a second, Margarito. That's one thing we can see about science, and that can be troubling, is that just because we don't have an answer to something doesn't mean everything is wrong. It just means that's the limit of what we understand now. Yeah, Margarito, what's up?
I was going to say about a dark matter lab underground in somewhere in North America.
Yeah, so dark matter at the scales at which we see it operate, a planet is not big enough to be elaborate, for something like that to exist. There's all sorts of experiments that are neutrino experiments underground and things like that might be modified to try and detect it, but again, it's not my field, so there very well could be something out there. I mean, I really should be honest about that. I'm not up on all the dark matter research labs. There are dark matter research labs probably underground. There's dark matter labs probably out in space, in the International Space Station. I know that doing precise measurement or precision measurement physics in space has been a rapidly growing, exciting field. So, I don't know where it's not. I guess what I should say to be more clear is that I'm not sure what experiments they think are going to be underground, because dark matter would not enter. My initial rejection, if you will, of the idea wasn't so much in the non-existence of a lab, but it's not clear that dark matter would interact with anything at the planetary scale, because it seems to not interact with regular matter at the galactic scale, right? And we've already seen that Earth is a negligible object on the scale of stellar objects. Forget galactic objects. So I'm sure there are laboratories trying to look at it, but again, it's so far eluded detection. So dark matter, we can see gravitational effects of objects in galaxies, stars, certain bright stars in galaxies that behave in a way inconsistent with the universe, just made of baryonic matter. And dark energy is an unknown form of energy. Again, this goes back to the car with the fuel, right? Where we see the universe is actually accelerating. It's getting faster, so we're seeing like a car accelerate, going faster and faster and faster, but we don't know where the source of that energy is coming from or why it behaves that way. And this is used to describe the expansion that causes the universe to accelerate. Again, we're just at the point of, this is the best we can do now. The future will hopefully illuminate dark matter and dark energy. Okay, but they're interesting things to think about. And one of the things I know in my field, for instance, is people are looking at interpretations and various theories, because when you see an observation like this, people start constructing theories. And then from there, you need to have not just predict the observation, but predict something else. And people are trying to eliminate these theories of dark energy and dark matter. So sometimes it's easier to say what they're not as opposed to what they are. So contents of the universe. So when you combine what we know about the standard model of particle physics with the observed energies we see, we find that based on our observations, normal matter can only account for about maximum 5% of the universe. All right. So another way to look at this is that every particle we interact with and every atom in our body, or the Big Bang itself, created all these stuff we look at, created only 5%. That was only 5% of the total. Normal matter is inside stars is about half of 1%. Normal matter outside stars is about 4.5%. So this is interesting and very approximate and very loose. Dark matter is thought to make up about 27% of the energy of the universe, and dark energy nearly 70 or 68%. All right. Now again, this is just based on the total energy required, sort of observed in the universe, right? We can observe energy associated with normal matter from its luminosity and its brightness. We can observe dark matter energy through motion of very bright Cepheid variable stars in galaxies and in supernovas from other galaxies. We can look at dark energy from looking at galaxies shifting, energetically looking at galaxies accelerating away from us, and sort of look at the luminosity and the mass and figure out how much energy it should take to accelerate all that mass that much. So we can get an idea of how much fuel should be required, but we can't find the engine or the fuel that's driving it. Okay. So questions, thoughts? Probably a good place to pause before we go into the evidence. That's the next thing we're going to talk about, is the evidence for dark matter. Okay. Oh, all right. Good. So let's keep going. So now, of course, as always, we want to talk about why do we think this way? Like, how do we know what we know? Which I'm hoping that, now that we're at the end of the class, that's a question. If there's one thing you take from this class, I really do hope it's just sort of always asking that question and accepting that sometimes there's a pretty good answer for it. You know, but also not being locked in any one way, and not crapping on, well, I guess that might be asking too much, not crapping on someone who sort of looks at it from another way, because we all do that from time to time. I'm no exception, certainly. I just saw an obnoxious YouTube video today. I won't get into it, but it's always upsetting when someone tries to present physics and says, everything you've heard about physics is wrong. This thing I say is the real physics. And it's like, no. You know, it just sort of sets up this circle of confusion for the most part for non-physicists. And then for physicists, you're just like, what is this person talking about? Why are they doing this? So anyway, back on track. Evidence for dark matter. What is the evidence for dark matter in galaxies? We want to see that. And we want to ask ourselves, we want to construct the argument for, does dark matter really exist? All right? And if it does exist, what might it be made of? So again, we're going to see the evidence for why the conclusions we draw are the ones we draw. And again, a lot of it comes down to Occam's razor. We've sort of constructed their, you know, astrophysicists and cosmologists have really constructed many scenarios, and this is the one that seems to be the simplest. All right, I want to emphasize that. It's not the one that must be correct, it's the one that seems most likely correct given our current observations. So, here's the big graph. This was the one that was available in my time, and this is the one that is available now. So let's take a look and understand this and give it some context. In order to understand what we're looking at here, we want to make a similar graph, which I'll make it's called an inset in the literature. So I'll make a blue set of axes. All right, so this is going to have the same thing. The x and y axis will be the same. This will be distance. So I'll call this d. Oh, no, I need to go to... That's also bad. I'll call this d, and this is orbital velocity. That's supposed to be a v. The only thing I want you to see is that these are the same, right? Orbital velocity, you have it written here. And distance, that's it. The scales will be different, right? So instead of thousands of light years, we'd probably have tens of millions of miles, right? But the same numbers. The numbers and all that won't be important. It's just the features. So in our solar system, I drew this before. If you look at the orbital velocities of, say, Mercury and the planets Mercury, Venus, Earth, Mars, Jupiter, and we got to the other planets, that's what the data looks like. All right, and we'll connect it with the theory. Shows that the farther you get away from, this is the sun would be here at 0, right? So that's the orbital velocity, that's the distance from the sun. Here we have the distance from the center of the galaxy, and we have the orbital velocity. Now, it's true that while galaxies are not centered like solar systems, right? And what I mean by that is that the center of mass is not right at the center of a galaxy. You would expect that as you leave the center of mass, right, as you get farther away from it, when you're clearly in those spiral arms, you would expect that at the you would expect weird stuff to happen in the short range, but long range behavior, you would very much expect to look exactly like this. All right, and that's due to our conservation of angular momentum. And in fact, I'll tell you this: we are now in the realm of looking at planets around other stars, and I'm pretty sure every planet follows every star system we've observed. We can also verify, and there's no reason it shouldn't, but we can also verify that angular momentum holds. So we're not looking at something exotic in these other places. And you'll notice that you go down and forward. Now, at the center of a galaxy, you'll notice that your orbital velocity starts increasing. So, but again, it's not a star. So we expect this to be a little bit weird, but you'll notice that we do get to this peak, and then, like I said, short range, we expect it to be different because the center of mass is more evenly distributed. But you'd sort of predict that you get to a point where now you're clearly sort of outside a disk region that's even the center of mass, and you would decay. And here's the funny thing. I want you to look at this region. You do. What we predict happens. We see it. So we see this region where you get farther away from the center of the galaxy, and the farther you get away from the central region of the galaxy, not the center, but it happens very quickly, right? So within a couple thousand light years, after you're out of the bulge, essentially, when you're in the disk, you get stuff that looks like it would in a star system. Now here's where things get interesting. You get this dip, and then it starts, as you get towards the end of the disk, it starts moving up again. All right, and as it moves up, you see that the orbital velocity starts increasing. This is not predicted with our conservation of angular momentum in baryonic matter, or based on our observations, based on the brightness of a galaxy, or of a whatchamacallit, of stars and galaxies. So maybe this is just a weird galaxy, but here's the odd thing. We start looking at other galaxies, and the behavior, they're different sizes, but we notice the same behavior, and sometimes even weirder behavior. I'm going to delete everything now because we're going to focus on these graphs. But we notice even stranger behavior, where we have that initial hump, and we go down, but sometimes it oscillates, and other stuff happens. So basically, either conservation of angular momentum is not true at large scales, or there's more matter out there than we can perceive. That's kind of the two things you have to ask yourself. And you have to analyze the data and see which conclusion seems more correct. Because there's huge consequences in both those, in taking either of those paths. And when looking at this data, I thought that maybe the conservation of that physics might just work at slightly different at scales, meaning there's effects that are very small on our scale that when you get out to these large scales would be more accurate. And that was called modified Newtonian dynamics. And what that told you is that took the angular momentum is wrong, or not conserved path. And what that led to was formulating that conclusion by modifying acceleration at large scales, or Newton's laws at large scales. That's why it was called modified Newtonian dynamics. And then you get new conservation principles and things like that that can give you the same results you get here, but don't involve new types of matter. However, Einstein's general theory of relativity and created a lot of problems with this modified Newtonian dynamics. And those two things couldn't reconcile. And general relativity, or that stuff we talked about space-time, is extremely successful at predicting new phenomena. So it became a bit of a contention. And we'll talk a little bit more about the other one, because that's the accepted side of it, which is that there's a different kind of matter that doesn't interact in normal ways with the matter we deal with every day. All right, so we saw these rotation curves. I explained them. So the mass, to take a look at it, the mass within the sun's orbit is about 10 to the 11, and the total mass is thought to be 10 times higher, or about 1 trillion solar masses. That's for the entire Milky Way. And basically, it's thought to be, the structure with dark matter is thought to look like this. You have your luminous matter with your halo stars and your disk, and then it's thought that there's a large dark matter halo that engulfs and encompasses the whole of the galaxy. Now, this being said, dark matter is thought to only interact gravitationally. What that means is that even though you might feel its pull, if there was a concentrated large amount of it around, it's more likely evenly distributed, and if you were inside a mountain of dark matter, you wouldn't know it, because it does not interact with you electromagnetically, which is how you experience the universe for the most part. Yes, you're bound to the Earth, but when you're looking at when you're undergoing chemical reactions by eating or touching something, there's repulsive forces. You know, there's forces of the mechanism by which atoms interact are these electrons inside them, or not inside them, but outside them. So a lot of your interactions are electromagnetic in nature, or atomic, but gravity just sort of keeps you sitting here by the planet. But to only interact gravitationally would make you, pretty much invisible and transparent. It could pass through you without any effect, all right? Because it has mass, but it doesn't have any of the properties that allow it to interact with what we'll call luminous matter, all right? Here. So we can measure orbital velocities in other spiral galaxies with a Doppler shift. We can see them moving. These, basically look at a Cepheid variable star. Well, you couldn't see it make rotations around its galaxy. That takes a long time. But we can see a galaxy. We can see the rotation of a galaxy because we can see stars on one side moving away from us, one side moving toward us. So we can see that spectrum get blue shifted and red shifted of certain stars. And that 21 centimeter line of atomic hydrogen sort of tells us all we need to know. We just look at the shift of that line. And all of these tend to have orbital velocities that remain constant at large radii, indicating large amounts of dark matter. So basically the idea is that the more you increase the dark matter, the more constant this part of the curve is. You'll notice UGC 2085 is very constant, but the ones down here are sort of wiggly, right? There's some wiggling going on here. So that's one thing, but there are others. Okay. So in elliptical galaxies, we can get that broadening of spectral lines will tell us how fast the stars are orbiting. Okay. So if we look at, we're looking at 3 spectral lines. So a wide line indicates that stars move fast relative to one another, and wider lines indicate that stars move faster relative to one another. So this will, looking at how this line will broaden out, will let us look at the velocities of stars in elliptical galaxies. Now remember, all this is just related to the Doppler effect. So basically, we know what we know about hydrogen. That gives us a good standard to look at, right? So hydrogen is our knowledge of hydrogen is some of the most precise of anything we know in the universe. And so it's good that it can give us all this information. So basically, we can look at these and conclude what the velocities must be based on the properties of these spectral lines. And that's it. There's the hard part is really gathering the data. Once you have the data, you can program it into a computer, and it'll dump out these answers pretty quickly. And it'll create a velocity distribution of galaxies, or of stars and galaxies, and you can see that the faster moving galaxies will be at the edge of the galaxy. All right. So we see that a lot of these almost all the galaxies we look at have dark matter. Now that being said, there are occasionally galaxies, and this is sort of I call this sort of the 4th test for dark matter, because it's really how should I say? It's really weird. There's a common saying that people say, the exception that proves the rule. So if you never found a galaxy without dark matter, you could be like, well, maybe we're getting something consistently wrong, right? Because we're saying, well, everything is dark matter, and then you start to say, well, okay, but we do find galaxies without dark matter. We find galaxies that have 0 dark matter because they behave exactly as you would predict if they had all baryonic matter. So we look at the brightness, we look at the mass, and they match instead of not matching, and then they behave exactly as models predict they would without dark matter at all. So they're the exception that prove the rule. And that's kind of terrifying to me, because that means there's something. It's like, if we had everything wrong, then two galaxies of the same luminosity would behave the same way, right? But they don't. It's creepy. Just creepy. It's crazy. So I don't know if you answered C, you were correct. Dark matter. So now this actually did exist when I was in undergrad, but I was a student, I was just learning. I didn't really understand the power of the connection of gravitational lensing with dark matter. So gravitational lensing is this effect predicted by general relativity from dark matter, which talks about the shape and properties of this lensing. And if you look, you'll notice this galaxy cluster is distributed kind of in a funky way, but the claim is that the dark matter would be uniformly distributed, and you'll notice that the lensing occurs in a circle like this from a uniform area. Now let's talk about what lensing is. So the idea is that this big thing of matter sort of acts as this lens. And here's what lensing allows you to do. So if you have a source behind here, right? Let's say it's a galaxy. I think there's a slide of this, but I'd rather just draw it. And say you have this light beam goes this way, this light beam goes this way. These should theoretically keep going on forever. So on Earth, a little us looking through our telescope here, I'll make a stick figure person. I'm not going to give them any arms. That's what they get. So the idea, what we can see is we shouldn't be able to see the light coming from this galaxy. But what happens in a lens is it changes the angle of the light so that these two rays can converge on Earth. And if they converge, they form an image, and we can see an image of the galaxy that's behind it, coming from two different places. All right, and that's what we see. And we see a lot of this. And this is a crazy effect. And again, you think about the scales of millions of light years that's taking for this lensing to happen. Or that this light gets separated from each other and then comes back together. It's pretty staggering, and it's a very interesting effect. But again, you're looking at a photograph here, not an artist's conception or anything like that. This is data, right? We see this, we have to explain it. And certainly with Newtonian gravity, right, with Newton, there's no explanation for this. This is a phenomenon that should not happen. But with Einstein, with general relativity, when we talk about space-time and things like that, it actually predicts that this should happen, which is a clear distinction between the two. And then the idea is to find areas of the galaxy, again, looking at fields this big, looking at gravitational lensing is something that only really, it's only about 25 years old, right? Before Hubble in the late 90s, we couldn't get pictures of the deep field like this, and let alone find lensing events. So this is all pretty new stuff, and I need my internet, my email to stop. So this was like cutting edge stuff when I was in college. And we were talking about it though, but like I said, it wasn't really my field, and I didn't, as I've grown, I've started to understand this connection a lot better. And it's like I said, it's a photograph. If I have a better theory, I've got to be able to explain this. And this was what modified even Newtonian dynamics could not predict this effect. So there was an attempt to make a general relativistic version of modified Newtonian dynamics, and that's where modified Newtonian dynamics fell apart. It could not come up with a predictive model that incorporated general relativity that worked. At least that's when I stopped following it, started checking up on it. Someone might have done more work on it, but I'm not aware. So again, the Doppler effect allows us to measure galaxy clumps and see what's related to what, and look at their velocities. And the mass we find in this velocity cluster, again, I'm going to draw the lensing. You'll notice if you draw a circle around here, you'll get the images of these galaxies. A lot of it's probably scattered by dust, but Some of it does get through. The mass we find from the motions in this galaxy indicate that the mass encircled in here is 50 times larger than the mass predicted from the luminosity. All right, so that's substantial. Now, this is pretty new, is that you can look at these clusters in large amounts of X-ray emitting hot gas, and the temperature of the hot gas can tell us the cluster mass. And when we look at the gas at the large scale, darn it if we don't get that it's mostly dark matter. Now, here's the thing. So between gravitational lensing, orbital dynamics, and analysis of X-ray clusters, we can get that there should be more matter than that there's large amounts of dark matter. Here's where it gets interesting, and here's where I finally got convinced. All three of these methods, three independent ways that don't rely on each other, they all give you about the same amount of dark matter. So that not only do they say there's more matter out there, right, but they all tell you that it's exactly the same amount of matter. And that in my mind makes the existence of dark matter pretty darn compelling. Okay? So this is a better picture of gravitational lensing. It sort of shows the real object, and then the image we see from the lens, from the galaxy cluster. And we can see that what you have to understand from optics is that the image, this looks like where it is, but we can tell from the lensing where it should actually be. And you can see the rays coming in and being bent by space-time, because that's what's bending here. And they come to Earth, and we can't see this galaxy behind the cluster, but we can see the images of the same galaxy around the cluster. Okay? So, I think there's a more fascinating picture coming up. Right, dark matter in a cluster. So, so not only do we see the image, but the lensing will cause part of making optical images is dealing with distortions. And the same is true with gravity, is we can see distorted, not only do we see the image, but we see distorted images consistent with lensing in these systems. Okay? So I can't play that illustration because we can't play things. That, I think, has been the biggest drawback to our semester online, is my lack of being able to play with a single. I can do it on my computer, but it doesn't like to share because it's all on the internet, and this thing goes a little crazy on the internet. So again, all three methods of measuring cluster mass indicate similar amounts of dark matter, and that's where you start to go, get pretty compelling. If they'd all measured different amounts of dark matter, well, that might have been more interesting, but it would have led to more confusion. Questions about the dark matter? Besides, does it really exist? We're getting there. Or questions, I guess I should say, about our evidence for dark matter. Okay. Well, I hope it's at least interesting. I know we're all sitting at home, and it's it might be a bit much, but hopefully it's at least it's interesting. Okay. So let's continue on for one of the bigger questions, which is, given all this, does dark matter really exist? Because you always have to allow that even if something looks good and looks right, I'll recall to the beginning of the semester that the Earth at the center of the universe looked pretty compelling, but ultimately it was incorrect. That could be true here, okay? And that's why we continue to do experiments to learn more, and to learn more about the universe, is because, we want to find out. And finding out is interesting because when you learn to detect new things and make new devices, that's kind of how new technologies form. you know, the basically one of the you know, computing was a developing field that was very niche until code breaking was required and nuclear decay rates were required, numerical approximations were required in the 1940s. Once those became two big things, that spurred on the development of a large number of scientists, right, a whole community, having to become familiar with computing. And then that just skyrocketed and exploded with the space race and the nuclear arms race. And now modern technology has a lot of this stuff has come out of defense spending. Like the internet, for instance, was originally something called it was developed in a from a military directive called DARPA as a way to communicate between military bases and then between universities and then eventually to what you see today. And often when these things are invented, their use isn't seen. It takes, you know, because not everyone can come up with the a original scientific theory. Very few people can, actually, but it's disingenuous to say that those are the people who can see the full impact of the thought that comes out of them. What I mean by that is it also takes another person to sometimes realize the amazing potential of an idea someone else had. One of my favorite examples of this is a very, very famous scientist named John von Neumann. Some of you have probably even heard of him. When he first saw the laser, said, "This is so cool scientifically. It lets us explore like quantum mechanics and cool stuff." But he says, "But there's no actual commercial application for this." He says, "You can't sell a commercial application." And there are innumerous commercial applications for the laser today. From sensing to map making to data storage. So if the person who invented the computer couldn't see the use of lasers in computers, it's like, you know, and he was considered like the smartest one of the greatest mathematicians of all time. So it takes different kind of minds to make humanity work. That's something to keep in mind. But when looking at does dark matter really exist, we want to look at, well, what our options are, what the arguments are, right? And again, that's how we kind of work with science, is we put up arguments that cover everything we can think of. So basically, it comes down to these two options. So if dark matter if dark matter either exists or it doesn't exist, right? So if dark matter, and you'll notice that gives us two options. So if dark matter exists, we are observing the effects of its gravitational attraction. You'll notice we haven't concluded that we know what it is, what it looks like, or anything like that. But if it does exist, then those become interesting problems. So if dark matter does exist, well, what does it look like? It must be something. If dark matter does not exist, then something is wrong with our understanding of gravity, causing us to mistakenly infer the existence of dark matter. And this is what I told you about modified Newtonian dynamics and things like that. However, gravity, or I should say general relativity, is extremely well tested. So the preference is option 1. All right? And like I said, I started as a young man here, and I now live here. Okay? So, and it's funny. So my favorite physics, well, not one of my mentors when I was an undergrad, he had a similar problem with the mass of the neutrino. So neutrinos, all experiments today show they have mass, but neutrinos from about the 1960s, the 50s and 60s, when they were first being really worked on, to the early 1990s, were assumed to be massless, and thousands of papers were written assuming the massless neutrino. And he said he was just sure it would be massless, but then it wasn't. And he even said, "I feel like it's wrong." He says, "I feel like there should be no mass in the neutrino. And my gut, everything inside my being tells me there should be no mass." And then he said, "But I'm wrong. The experiments don't agree with me." And that's what happened here to me with dark matter. So let's see here. That's not being helpful. It's a pretty picture, but it's not. It's just explaining the X-ray emission stuff again. So in order to look at dark matter, I don't know if you know what you're looking at here, But basically, this is a picture of the particle accelerator, the Large Hadron Collider in Geneva, Switzerland, otherwise known as CERN internationally. And so basically, this is the most expensive scientific instrument in the world. All right, it's 22 kilometers long, and it has to be aligned to within a micrometer, or to better than a micrometer, right? So that means that everything has to be perfectly in a straight line down to 0.0000 1 meters. All right, for the whole 22 kilometers of the circumference. Now, all this is underground, so and it's all very well shielded. And this is what is used to investigate those crazy high energy levels of the universe, like where the weak nuclear force and the electromagnetic force can recombine. A lot of that is done here. So if dark matter is a particle, it's thought that it will be detected in something like this. Now, moving on. How dark is it? Well, it's certainly not as bright as a star, otherwise we'd see it. Now, there's two basic options, and you'll notice they're very culturally opposite of each other. So the thought is that maybe dark matter is ordinary matter that we can't see. And these are often called massive compact halo objects, or machos. These are dead or failed stars in halo galaxies. And then we have the other interpretation is exotic particles, right? So if dark matter exists, it's got to be either ordinary stuff we just can't see, or something else entirely different, right? Now, these would be called weakly interacting massive particles, otherwise known as WIMPs. So it's machos versus WIMPs. I find that without understanding much of these two, our cultural dispositions have us rooting for machos. But in fact, we're going to see that the WIMPs will take the day here. So when we look at it, the best bet is the WIMPs. And let's look at why. So compact star-like objects occasionally make other stars appear brighter through lensing, right? So there would have to be, if machos were the correct answer, there would have to be a bunch of stars we can't see directly, but we should be able to see their effects indirectly through lensing, right? And we do see this. So we can see this through stars. We can observe lensing from stars. And if there's 10 times as much mass than we can normally see, we'd expect a ton of lensing events to be observable. But there are not nearly enough lensing events to explain all the dark matter. All right? So why WIMPs? There's just not enough ordinary matter, no matter how much way we cut it, for machos to be true. So WIMPs could be left over from the Big Bang, and models involving WIMPs also explain how galaxy formation works. So WIMPs are starting to when we put them in calculations, give us galaxies that look more familiar than machos as well. This makes them a more compelling explanation, but right now we have, we have been and are in the process of trying to figure out the true nature of dark matter, and it's actually been sort of an exciting field, an active field for as long as I can remember, for most of my life, because as we get more precision measurements, which is the field of physics I'm in, more physics measurements opens up new regimes of measurement to test new theories of things like dark matter and what we'll see, dark energy. Okay, so we've learned lots of things. That's great. So we want to see structure and formation of the large-scale universe and see the role that dark matter plays. Okay, so here we have the Laniakea Milky Way colors coordinate. The Laniakea local supercluster. So basically, the Laniakea supercluster is about 100,000 galaxies. The Milky Way is here on the outreaches, that are all attracted to something around here called the Great Attractor, all right? And basically, the Pisces superclusters are twin. things outside this circle are attracted to another great attractor. And we can get these distances again as shifted, inferred from redshifts. And we can see, you'll notice that everything sort of gets squeezed into these arms that sort of flow in. You see this illuminated stuff coming in here. All right. So the claim here is that gravity of dark matter is what caused protogalactic clouds to contract early in time. So the thought is that in a more dense universe where you have these clouds, it was really individual dark matter clouds that caused local galactic clouds to collapse and form galaxies. So WIMPs can't contract to the center because they don't radiate away their orbital energy. So that means that the dark matter, and that's interesting, right? So it's thought that a galactic cloud before it collapses would be the size of the dark matter halo. The normal matter will collapse to the center, but the dark matter will stay outside because it can't interact with light, which means it can't radiate away its energy. So it just sort of stays suspended forever, I guess. I don't know. It's weird. Dark matter is still pulling things together, and after correcting for Hubble's law, we can see that galaxies are flowing towards the densest regions of space. So that's, again, what I talked about, that great attractor, which is a very interesting region of space that is still a hot topic for research. But this also sort of seems to explain some of the large-scale structure of the universe. You know, there are these structures of galaxy clusters that appear to be all connected, like the Sloan Great Wall, which can be in the billions of light years big. And you can see the galaxy distribution is a little more uniform here. But as we get into lower sections, it can be a lot denser. All right. Okay. Basically, when we look at these things, you'll notice we have clusters of galaxies. I want you to look at the dense parts here. You'll notice you have these clusters of galaxies and these sort of big empties in between them. So we have superclusters and voids. All right, and voids are sort of sad. You know, superclusters have tens of thousands of galaxies or thousands of galaxies all sort of next to each other, and voids can be very large empty regions that have only a handful of galaxies in them. And there's some voids that have nearly nothing in them at all. So when we look here in the expanding universe, we can see at 0.5 billion light years, this 13 million light years here will be expanded over the next 13 billion years. We have expansion, so you notice that 13 million light years becomes 140 million light years. So we've expanded by more than 10 times. And the dark matter, the local dark matter, has sort of squeezed everything into this cosmic web that you see. Okay? And so we can see that as the box is expanding, everything gets sort of squeezed in. Okay. So WIMPs sort of describe WIMPs describe all of that stuff, the galaxy formation and distribution. But now we want to move on. I think before we move on to dark matter or dark energy and the fate of the universe, I think we'll just take a slight 10-minute break. We won't take a long break, but it's been about an hour, and it's good to sort of rest one's mind from that. And also do keep in mind that dark energy is pretty much our last topic, and then we'll watch our video on the death of the universe, and then that'll pretty much be it. So I'm not expecting us to go much past 5:30, 5:45. All right. So I will be back. Okay, we're back. Let me see something here. And then I'm going to take one picture in case that's just, it's good precaution. All right. Okie dokie. Okay. So now we're going to talk about dark energy and the fate of the universe. So we'll sort of start. We started our discussion of the universe with the baby universe, and how it got to be the universe we see and experience today, and we'll try to project out into the future. Dark energy will give us some indication in what the later stages of the universe will look like. And there's a video I like to show on the last day of class that I find is a suitably depressing end to talk about the end. So anyhow, but in order for all that to make sense, we want to talk about dark energy and the fate of the universe. Now, pre-2000, so when I was in high schoolish, say, there were thought to be, the great argument was, can we get new data? So let's say pre-1997, there were thought to be 3 situations of the universe, which was either a coasting universe that sort of just kept expanding in this linear fashion forever, a recollapsing universe that would lead to a big crunch, or a critical universe that was just, that they'd call just about flat. Because you see, even a coasting, you might say, well, wait a minute, why is this critical and that's coasting? Well, coasting universe still indicates a negative curvature, all right? So remember we talked about curvature in our last chapter about negative, positive, and flat. And these are basically your 3 curvatures here, all right? So we're still at what we'd call a critical density, but each of these slices, you'll notice they look from the past, sort of we have the same thing, but it's what are we going to look like in the future. All right. So let's see here. So right. So the fate of the universe will depend on which one of these is true. You'll notice that we're starting with these 3. So lots of dark matter would mean that there's enough dark matter to eventually pull everything back in and recollapse the universe. However, there is a problem with this, which is that it's not clear where the energy that's if the universe is a closed and contained system, it's not clear where the radiated energy goes from this big crunch. There's something called the second law of thermodynamics that says you can't recover heat energy. So this has always had issues and a lot of detractors. Although some people talk about it like it's a viable solution, it's not really one that we're going to have. Again, not enough dark matter would lead to a coasting universe, which would be a whatchamacallit, a negative curvature universe, and that would just go on forever. The critical density, though, remains basically a flat structure. But things got interesting in the 2000s when we found that none of those are right, that in fact the correct description is a accelerating universe, but at a critical density. So our universe sort of looks like this one up to here, but then will accelerate out here, okay? And so we want to look at some stuff where this data comes from. So the amount of matter is around 25% of the critical density, which suggests at the very least the fate of it. I thought we were really close to the critical density. No, because we're flat. Hold on. I think I was wrong there. I'm going to have to edit all that out. Okay. I mixed up curvature of space-time with just the expansion of the universe. All these represent the criticalness of a No, that because I'm right there. A closed universe would. No, I'm not right. I'm not right there. Okay. I'm not completely wrong, but I want to restate it again correctly. Because before we were talking about the curvature of space-time, the universe as a curved space-time object, we're still talking about that flat universe here. You'll notice in each picture. But now we have how this disk expands or doesn't expand. And we're going to find that the expansion of the disk of this flat universe, which means structurally flat, is going to be actually accelerating. And that will depend on the density of dark matter. All right, or the density of matter. So the amount of matter is 25% of this so-called critical density, suggesting eternal expansion. So now we're good, we're on the right track. But our expected result is that we would have that linearly expanding universe, right? Where we just have these straight lines. But we have this curve of acceleration. Okay, and so again, just like we had with our car metaphor, in order to have something accelerating, there's got to be a fuel source, right? And so that fuel source is dark energy, and so we can see the effects, we can observe the effects of dark energy through Doppler shifts of galaxies. That indicates that this dark energy is there, but again, we can't see the source. We don't have a reason for it. So the estimated age of the universe will depend on both dark matter and dark energy, and it is from the WMAP satellite that really lets us map dark energy that gives us an age of the universe to be about 13.7 billion years old. All right? And that's just looking at some supernova data. So basically, we look at collections of supernova data and match it to theories. So we can see the theory in the past for critical, coasting, accelerating, and our recollapsing universe. Now I want you to notice that the present, so I'd say these are in billions of years in the past, so all of human history and our ability to measure things takes place right around here. So you'll notice all of the theories match about here. But as we get more data into the past, we'll notice very quickly the recollapsing model falls away, and you'll notice the critical model, we're kind of not even really close, right? That one falls away too. So the only ones that really, make the most sense is sort of between supernova, an accelerating universe, and a coasting universe. Now the coasting universe used to have a 14 billion year old, like a 14.5 billion year old intersection here with the zero line. But you'll notice the accelerating universe sort of curves and dips right down here at 13.7. So most of the data as we go back in time the best fits are on the accelerating curve. And so that's where the conclusion comes from. So again, that hopefully will give you insight into sort of the many predictions we have, and the fact that at this current point in time, they're all very similar, right? They match up pretty well. So it's only by looking back in time, we're using things like the Hubble Space Telescope and looking at distant supernova, that we can get more data and rule out a coasting or a critical or a recollapsing universe. All right, so those are really effective. Even though people still talk about these things, they really have been effectively ruled out by supernova data as possible. Now, it's possible we are making huge mistakes and don't understand everything at a fundamental level, I suppose, but again, a lot of experiments keep coming out as you'd expect them. So, again, I made that error, which I'm going to forgive myself for because I'm not an astrophysicist, of looking at the geometry versus the expansion rate of said geometry. All right, the geometry itself we looked at is flat. We talked about that kind of curvature. All right, so observations tell us that the density of the universe is equal to the critical density, but we can only account for 30% of that with regular matter. So basically, when we look at our matter density, we only get 30% of that matter, and then the other 70% gives us how much dark energy there should be. Now, that doesn't really tell us why it should be flat. Now I'm wondering if I wasn't incorrect. Incorrect about being incorrect. You'll find Albert Einstein even got confused with all this stuff. So Albert Einstein invented something called the cosmological constant, which has been a compelling little piece of research, and he thought introducing it was a blunder, and it turned out it turns out to not have been a blunder, but not for the reasons he originally thought. So it's, fun times, fun with science. But basically, we're looking at what we're really concentrating here on is the dynamics of the universe expanding. And sort of the short message of dark energy is we can observe space accelerating, that the velocities of these galaxies are accelerating, right? And to look at the flat structure we observe, dark energy has to account for 70% of the universe. So that's how we get that conclusion. It's based on the flatness that we look at. That's just got to be, in order for dark energy to be a large part of the universe, dark matter, all the matter we look at, only gives us 30% of the density we need. We get the 70% from, and looking at the acceleration, looking at the rate of acceleration to maintain the flatness that we still continue to observe. Because again, if you take something, you'd expect you to be able to have ways to find curvature eventually, if it were there at all, right? As it gets bigger. So the fact that the universe remains so flat is indicative of the of how much energy we need for dark energy. And again, we can observe this acceleration. I wish I knew more about dark energy. Like I said, I know that certain interpretations of dark energy have been eliminated. So that's sort of what goes on with that field of research, is people say, well, how could dark energy work, right? And there's a lot of different ideas of how dark energy could work. And in the precision measurement world, they have eliminated a large swath of dark energy theories by making predictions at a small scale level and showing that those could not be true based on experimental evidence. So interesting stuff, interesting stuff. But otherwise, that's it for this part of it. That's our last slide of our last chapter. Everything goes into summaries from here. And now we want to watch a video on what is the fate of the universe. So I'm going to stop recording, and I'm going to send you the link, and we can just sort of sit and we can discuss